Hello everyone, welcome to the second part of the topic, that is retina anatomy with respect to OCT imaging. In the first part, we spoke about the basics of OCT imaging and retina anatomy. In this video, we'll speak about the layers in details. The first layer, infest to us clinically, is the internal limiting membrane. This forms the innermost layer of the retina and the outer boundary of the vitreous. It is represented by the intermittent hyporeflective thin line in OCT. Both the retina and the vitreous contribute to the formation of this membrane, which consists of four elements: collagen fibrils, proteoglycans, which is mostly hyaluronic acid of the vitreous, the basement membrane, and the plasma membrane of the Mueller cells and possibly other glial cells of the retina. In flat preparations of the retina, the external portion of the internal limiting membrane exhibits a mosaic pattern and depicts the irregularities of the foot processes of the Mueller cells. It continues uninterrupted at the fovea, where it is thickest, but is absent at the edge of the optic disc. At the periphery of the retina, the membrane is continuous with the basal lamina of the ciliary epithelium. The inner portion of the internal limiting membrane is also known as the hyaloid membrane of the vitreous. Vitreous has a firm attachment to the retina at the optic disc, the fovea, and the ora serrata. The side at the fovea is more weak. Right below the internal limiting membrane is the nerve fiber layer. This is represented by a hyperreflective band in OCT. The nerve fiber layer contains the axons of the ganglion cells, which is known as the afferent fibers. It also contains glial cells, a rich capillary bed, and centrifugal or efferent fibers. The axons are arranged in arcades delineated by the processes of the Mueller and other glial cells. Now, if we look into the schematic representation of the course of the nerve fibers to the optic nerve, the afferent fibers take a radial course parallel to the inner limiting membrane and converge on the optic nerve. These fibers are distinguished as the papillomacular bundle. The axons originating from ganglion cells temporal to the fovea take an increasingly arcuate course to bypass this region. The superior and inferior fibers are separated at their origin by a horizontal raphe that extends from the fovea to the extreme temporal periphery of the retina. The nerve fiber layer is thickest at the nasal edge of the disc. The next layer is the hyporeflective, the ganglion cell layer. It is composed mainly of the cell bodies to the third order ganglion cells. Other elements such as processes of Mueller cells, other neuroglia, and branches of retinal vessels are also present. The ganglion cells form a single layer in the peripheral retina. By two layers are formed at the temporal side of the optic disc and 6 to 8 layers at the edge of the fovea. And the ganglion cell layer is absent. The next hyperreflective layer is the inner plexiform layer. This layer marks the junction of the second order neuron, the bipolar cells, with the third order neurons, the ganglion cells. The inner plexiform layer is thicker, has more synapses per unit area, and contains a greater variety of synapses than the other plexiform layer. The inner plexiform layer is absent from the foveola. In addition to the synaptic connections among bipolar, ganglion, amacrine, and interplexiform cells, the inner plexiform layer also contains processes of the Mueller cells, an abundant microvasculature, and an occasional displaced nucleus of a ganglion or an amacrine cell. The next hyporeflective layer, the inner nuclear layer, consists of 8 to 12 rows of closely packed nuclei of the bipolar cells, horizontal cells, amacrine cells, interplexiform cells, and supportive Mueller cells. 4 layers can be distinguished by light microscopy: horizontal cell nuclei, bipolar cell nuclei, Mueller cell nuclei, and amacrine and interplexiform cell nuclei. The outer plexiform layer, which is represented by a hyperreflective layer in OCT, marks the junction of the first and second order neurons in the retina. The outer two-thirds of this layer is composed of the inner fibers of photoreceptors surrounded by processes of the Mueller cells, and the remaining one-third consists of the dendrites of the bipolar and horizontal cells, as well as Mueller cell processes. The outer plexiform layer is thickest at the macula and consists predominantly of oblique fibers that have deviated from the fovea. The inner fibers in the outer layer represent the axons of the rods. The seventh layer is the hyporeflective outer nuclear layer, which lies internal to the external limiting membrane and contains the soma and nuclei of the photoreceptor cells. Nasal to the disc, the outer nuclear layer is thick and has 8 to 9 rows of nuclei. At the temporal disc, only 4 rows of nuclei are present, and in the fovea, the 10 rows of cone nuclei increase the width of the outer nuclear layer, known as the Henle's fiber layer. Macular star follows the radial pattern of the exudates, and it is an important structure in the retinovascular disease. The intraretinal fluid or the retinal cysts are formed in front of the Henle's fibers layer. The next hyperreflective boundary is the external limiting membrane, which separates the layer of rods and cones from the overlying outer nuclear layer. It extends from the optic disc to the ora serrata, where it becomes continuous with the basal lamina between the pigmented and non-pigmented portions of the ciliary epithelium. It is not a true membrane because small molecules pass freely through the junctional complexes. The main functional implications of the external limiting membrane include providing a selective barrier for nutrients that pass between the adjacent Mueller cells, as well as stabilizing of the position of the transducing portions of the photoreceptors. Now the next layer is one of the most important layer in the retina, the layer of rods and cones. But before we move forward, we have to understand the anatomy of the inner and outer segments. Extending from their cell bodies, the photoreceptors have two morphologically distinct regions, the inner segment and the outer segment. The outer segment lies embedded in the interphotoreceptor matrix, just internal to the retinal pigment epithelium. Its major function is the conversion of light energy into electrical impulses that are propagated through the neural retina and along the optic nerve to reach the visual cortex in the brain. The outer segment is attached to an inner segment through a cytoplasmic isthmus, which is specialized cilium. Now if you look closely into the photoreceptor layer, we would find 3 different bands with different reflectivity. The first hyporeflective band is just below the external limiting membrane and is known as the myoid zone, which is composed of the fine granular cytoplasm of the photoreceptor cells. The second hyperreflective band is known as the ellipsoid zone, which is composed of the mitochondria of the photoreceptor cells. And the third hyporeflective band is composed of the outer segment of the photoreceptor cells. It contains stacks of flattened double lamella in the form of discs. The RP consists of a single layer of approximately 5 million cells, firmly attached to its basal lamina, the lamina vitrea of Bruch's membrane. The microfibrils that originate from this lamina extend into the lamina elastica of Bruch's membrane. The apical region of the RPE is only loosely adherent to the sensory retina. The absence of specialized adhesion molecules such as laminin and fibronectin in the interphotoreceptor matrix and the lack of junctional complexes between apical microvilli of pigmented epithelium cells and the outer segments of the photoreceptors leave the sensory retina prone to detachment in pathological conditions. Thank you. If you like the video, please share, like and subscribe.